Hi, my name is Mel, and I do a lot of videos on tech subjects, evolution, science, different things. What interests me, I'm in IT and cybersecurity, so there are a lot of my videos about that, but occasionally do others. Okay, so I'm going to be talking about CPU, or Central Processing Unit. Okay, so the CPU is part of the computer that does the thinking. It follows instructions, makes decisions, and performs calculations. Everything your computer does, like opening apps, loading websites, running games, ultimately passes through the CPU. So there's three core jobs that it does. Number one, fetch. It grabs an instruction from the memory, like RAM. It decodes. Step two, decode. It figures out what that instruction means, like add numbers, move data, compare values, so on. Then step three, execute. Performs the action and sends the result where it needs to go. The cycle repeats billions of times per second. The CPU is called the brain because it processes all instructions, coordinates with other components, handles all logic and decision making, keeps everything in running order. But it is not smart on its own. It just follows instructions extremely fast. So key parts inside a CPU. Okay, so even though a CPU is fairly small, it contains specialized sections. Some of these are cores, which are mini CPUs inside the CPU. The more cores, the more tasks at once. So I would normally get people get at least a 4-core CPU, 8-core, depending on what you're going to need it for. Cache, this is still inside the CPU. There's another area called a cache. Super fast memory that's built into the CPU. The ALU does math and logic. The control unit directs traffic inside the CPU. So how this fits into the whole computer. The CPU decides what should happen. The RAM holds the data the CPU is working on. Storage, which is like SSD or HDD, handles long-term files. The GPU, or graphics processor unit, handles graphics. The motherboard connects everything. The CPU is the coordinator. Okay, so what actually happens inside a CPU? So the first thing is cores. As I said, the more cores, the better. Each core is a fully functional mini processor. Say a 4-core CPU can work on 4 tasks at once. An 8-core CPU can handle 8. The more cores, the better multitasking and parallel workloads. As I said, I reckon an 8-core would be minimum these days. ALU, which is an arithmetic logic unit. This is the part that does the math and the logic, addition, subtraction, comparisons like greater than, less than, equal to, bitwise operations. Every calculation in every program eventually passes through the ALU. The FPU, the floating point unit, handles decimal and scientific calculations, which is essential for graphics, physics, simulations. Audio GPUs have thousands of FPUs for this reason. So every GPU, which is graphic processor unit, has lots of floating point units for this reason. The control unit, the traffic controller, okay? It tells the ALU, which is their arithmetic logic unit, what to do, manages the flow of instructions, coordinates everything inside the CPU. Then there's the registers. The CPU's private ultra-fast memory holds the data the CPU is using right now. It's much faster than RAM and used for calculation, addresses, and counters. Cache, which is L1, L2, L3. This is where the CPU stores frequently used data so it does not have to wait for RAM. L1 is tiny but extremely fast. L2 is larger and slower. L3 is shared between cores, bigger and slower again. So how does the CPU actually run instructions? So we've gone through this before, but I'll go through it again. The instruction cycle. 1, fetch, get the instruction from memory. 2, decode, figure out what it means. 3, execute, perform the operation. 4, store the result or save the result. And this is repeated billions of times per second. Pipelining. Instead of doing one instruction at a time, the CPU overlays them in an assembly line, or like a one instruction is being fetched, another one is being decoded, another is being executed. This massively increases throughput. How does the CPU talk to the rest of the computer? The CPU obviously does not work alone. It relies on the system around it. So RAM holds the data and programs the CPU is actively using. If RAM is slow or full, the CPU waits. Storage, which is SSD or HDD. Long-term storage. Programs are loaded from here into RAM and then on into the CPU. The motherboard is the communication highway. The CPU uses buses and controllers to talk to RAM, storage, GPU, and peripherals. The GPU handles graphics and parallel workloads. The CPU delegates heavy visual tasks to the GPU, which is graphic process unit. Why clock speed matters. Clock speed, like for example 3.5 gigahertz, tell you how many cycles per second the CPU can run. But it's not everything. Architecture, cache, and core count matter just as much. Right, so obviously the higher the clock speed is better, but like the better the cache and the core and the architecture is, better it is as well. So the whole picture, the CPU is a highly optimized machine for executing instructions, performing calculations, and coordinating the entire computer. It's fast because it uses pipelines, caches, registers, and multiple cores to keep work flowing without waiting. And like, I'm just going to go through what happens in a CPU with a single instruction. Say, for example, a program wants to do 5 plus 3. Okay, so this is one instruction. Inside the CPU, this becomes a tiny, precise sequence of electrical operations. The program, so first, the program is fetched. The program counter holds the memory address of the next instruction. The CPU sends the address to RAM. The RAM returns the instructions like add R1, R2, R3. This instruction moves into the instruction register or IR. Okay? The instruction, so step 2, the instruction is decoded. The control unit reads the instruction and breaks it into parts. The operation add, the source registers R2 and R3, the destination register R1. So the control unit knows which circuits to activate, which registers to read, which ALU function to use. Then number 3, the operands are loaded. So registers 2 and 3 already contain the numbers 5 and 3. These values are sent into the ALU's input lines. Step 4, the ALU performs a calculation. So input A, so the ALU receives input A, which equals 5, input B, which equals 3, and their operation equals add. Inside the ALU, tiny logic gates and or XOR NOT combine to perform binary addition. The result becomes output equals 8. The ALU also sets flags. 0 flag, is the result 0? No. Carry flag, did it overflow? No. Sign flag, is it negative? No. These flags help with future decisions like if statements. The result is stored. The ALU sends a result 8, which is the result is equals 8, to the register file. Register R1 is updated to hold the value 8. The program, so step 6, the program counter implements. The CPU updates the program counter or PC to the next instruction. The cycle repeats. So this entire process, fetch, decode, execute, store, happens in one clock cycle or a few cycles depending on the architecture. At 3.5 gigahertz, that's 3.5 billion cycles per second. Billions of these tiny add, compare, move operations combine to create games, browsers, operating systems, AI models, and everything you see on a computer. All right, so this is sort of like I'm trying to sort of give basic examples here. So I want to talk a little bit more about how the ALU, or the arithmetic logic unit, inner workings within a CPU actually performs binary additions. The APL doesn't know numbers like 5 or 3. It only works with bits, as in a 0 or 1. It works with binary and uses simple logic gates to combine them. Add 2 binary bits, or 2 binary digit bits. The CPU uses a circuit called a full adder. A full adder takes bit A and bit B, carry in from the previous bit, and produces sum and carry out. For the logic gate involved, a full adder is built from XOR gate and exclusive OR, AND gates, OR gates. These gates are the unquote atoms, or the basics of digital logic. How a single bit is added. Let's add 2 bits, A and B. Step 1, exclusive OR for the sum. The XOR gate outputs 1 only if the inputs are different. So 0 exclusive OR 0 equals 0. 0 exclusive OR 1 equals 1. 1 XOR 0 equals 1. 1 XOR 1 equals 0. So it's basically comparing, all right? It only outputs 1 if the inputs are different. This gives an initial sum before considering carry in. And 2, step 2 for the carry, the AND gate outputs 1 only if both inputs are 1. So 1 and 1 equals 1, anything else equals to 0. This produces the carry out. Add the carry in, the initial sum is exclusive ORed again and with the carry in, and the carry out is updated using all gates to combine all carry sources. Putting it together, adding 5 plus 3. So 5 in binary is 0101. Okay, it's a 4-bit byte. 3 in binary is 0011. So we add it from right to left. So from right, okay, this is from here to here. So from right to left, 1 and 1, so bit 0, 1 plus 1. Sum equals 0, carry equals 1. Bit 1, 0 and 1 plus carry 1. 0 XORed, which is exclusive of 1 equals 1. 1 XOR carry 1 equals 0. New carry 1. So you've got to carry it, all right? Bit 2, 1 plus 0 plus carry 1. So the same thing, okay? And bit 3, 0 plus 0 plus carry 1. 0 XOR 0 equals 0. 0 XOR carry 1 equals 1. New carry equals 0. So the final result is 1, 0, 0, 0. So 1 and 3 zeros, which is 8. Okay, this is all done by tiny gate switching on or off. Every CPU instruction, adding, comparing, looping, branching, is built from these microscopic operations. All right, so this is how this basically operates, all right? Thank you.